Hello everyone, I am Dr.VRAO-PHYSICAL, Associate Professor and your Chemistry Learning Companion. Welcome back to our channel. In the last video, that is Introduction to Quantum Mechanics Part 1, we came to know that the subject physics paved the way for quantum mechanics, and de Broglie's hypothesis bifurcated the subject physics into two major branches, that are classical mechanics and quantum mechanics. Moreover, we came to know that classical mechanics is a branch of physics that deals with the macro objects where Newton laws holds good, right? And coming to the quantum mechanics is a branch of physics that deals with the micro objects associated with wave nature where Newton laws not holds good, right? This is what we learned in the last video, right? In this video, we shall learn what is de Broglie's hypothesis, right? What is de Broglie's hypothesis? De Broglie proposed a hypothesis that all microparticles, including electrons, moving with high speeds are associated with wave nature. I repeat, all microparticles, including electrons, moving with high speeds are associated with wave nature, right? Based on this hypothesis, one can admit that electrons revolving around the nucleus in a Bohr's orbit must be associated with the wave nature. I shall draw the Bohr's orbit, right? Right. I shall draw the Bohr's orbit, right? I shall draw the Bohr's orbit, in which usually we learned that from the previous knowledge, that with the previous knowledge that we have, electron revolving around the nucleus in a circular orbits, in a circular orbits, in a circular orbits, right? This is the perception that we have until before the advent of de Broglie's hypothesis, right? Before the advent of de Broglie's hypothesis, all we perceived that, all our perception is that electron revolving around the nucleus in a circular orbit, in a Bohr's orbit like this, right? Electron revolving in the Bohr's orbit like this, right? But de Broglie proposed a hypothesis that, right, all microparticles, including electrons, moving with high speeds are associated with wave nature. So from this hypothesis, we can one can admit that this electron, the electron revolving around the nucleus, is associated with the wave nature, right? We can see that wave nature in the next slide, right? Right, right, right. We can see the wave nature of the electron, right? So you can see the wave, electron wave, that is up to this time and before the advent of de Broglie's hypothesis, electron revolving in this circular orbit, in this circular orbit, in this circular orbit, but in this circular orbit, in this circular orbit, right? But after the advent of de Broglie's hypothesis, this electron behaves like a wave because this electron is associated with the wave nature, right? And moreover, de Broglie argued that, right, this is the wave, right? This is the wave motion of this electron wave. This is the wave motion, right? This is the wave nature associated with the electron, right? Right? This is the wave nature associated with the electron, right? And moreover, de Broglie argued that this electron wave de Broglie argued that this electron wave behaves like a standing wave because it does not travel. Okay, whenever, as long as that electron revolving around the nucleus, the electron wave or the wave nature associated with the electron, right, or the that wave or that electron wave, simply we call it as electron wave, right? That electron wave behaves like a standing wave as it does not travel, right? So henceforth we call this electron wave as standing wave or electron wave. Okay, whatever in whatever the way you are convenient, you can call it as electron wave or standing wave, right? Right. And de Broglie argued that the length of this electron wave, the length of this electron wave, the length of the electron wave, right? The length of the electron wave, n lambda, right? The length of the electron wave, n lambda, is equal to the circumference of the this circular orbit, right? I repeat, Bohr argued that the length of this electron wave, the wavelength of this electron wave should be equal to circumference of this circular orbit, which is given by n lambda is equal to 2 pi r. If this wavelength of this electron wave is equal to circumference of this circular orbit, that is n lambda is equal to 2 pi r, then that wave is called in phase. That wave is called as electron wave in phase, right? Which leads to constructive interference, right? Which leads to constructive interference. Okay, I shall explain the what is constructive interference, what is destructive interference in the another video, right? Okay, so when n lambda, that is length of the electron wave, is equal to 2 pi r, that is circumference of the circular orbit, then this stationary wave is called, stationary wave is in phase, right? And if this length of the electron wave, that is wavelength of the electron wave, not equal to, if it is not equal to, that is length of this wavelength of this electron wave not equal to circumference of the circular orbit, then that stationary wave is in out of phase, out of phase. Okay, you need to differentiate the two terms. Okay, stationary wave in phase and stationary wave out of phase. How can we differentiate the wave which is in phase and which is in out of phase? For example, you see, right? This is the wave. Okay, this is the wave, and this is the called crest, and this is called trough. This is called crest. This is called trough. This is called crest. This is called trough. Okay, we can observe consecutive crest, trough, consecutive crest, trough, crest, trough, crest, trough. Okay, when we find consecutive crest or trough, that wave is called in phase wave. Okay, whereas when you observe this standing wave in the out of phase, where you can observe crest, trough, right? Again crest, again crest. Okay, consecutive series is disturbed. Okay, you can observe this. Okay, so again I shall explain again. Okay, this is the crest and this is the trough. Again crest, crest after we need to get a trough, but again crest. Okay, so again trough, okay, again crest. Of course, this series will be followed after this point, but we get a crest after crest. Okay, that indicates that wave is in out of phase, and that wave in out of phase leads to destructive interference, right? Okay, therefore, so de Broglie argued that the electron, which is revolving around the nucleus in a circular orbit, behaves like a wave. That's why we call it as electron wave, and this electron wave, wavelength of that electron wave should be equal to n lambda is should be equal to circumference of the circular orbit. If it holds good, that is n lambda is equal to 2 pi r, then it is called stationary wave in phase. If it is not equal to n lambda is not equal to 2 pi r, that is called stationary wave in out of phase, that leads to destructive interference, right? Right. Then I shall explain the terms in that equation n lambda is equal to 2 pi r, right? Right. That equation n lambda is equal to 2 pi r. N lambda is equal to 2 pi r, where lambda represents the de Broglie's wavelength. Where lambda represents the de Broglie's wavelength. Where lambda represents de Broglie's wavelength. Where lambda represents de Broglie's wavelength. Right, where lambda represents de Broglie's wavelength, right? R represents the radius of the electron's orbit, and n is an integer, and it can take the values 1, 2, 3, right? From this, it follows that R can only have certain values as n increases from 1 to 2, 2 to 3, and so on, right? And moreover, you need to keep this point in your mind that since the energy of the electron depends on the size of the orbit, okay, how can you conclude this energy of the electron depends on size of the orbit? From the Bohr's relation, energy En is equal to minus 13.6 by n square into z square electron volts. Okay, this is the Bohr's energy equation. Okay, by changing, okay, since the energy of the electron depends on, from this equation we can conclude that the energy of the electron depends on size of the orbit, right? So its value must be quantized. Okay, its value must be quantized, right? Okay, so these are the terms, okay, now these are the terms in this equation. Now let us go further, right? Let us go further. Right, so based on this assumption, or based on this hypothesis, Bohr proposed a wavelength for this electron wave. Okay, already we came to know that de Broglie proposed that the electron, which is revolving around the nucleus in a Bohr's orbit, is associated with wave nature. Okay, that is the de Broglie's hypothesis, and he moreover he proposed that the length or the wavelength of that wave, stationary wave, is equal to circumference of the circular orbit. N lambda is equal to 2 pi r. Okay, based on this assumption, or based on this hypothesis, de Broglie derived a wavelength for this electron wave. Okay, which can be derived a wavelength for this electron wave. You can see that wavelength, the wavelength that is derived by de Broglie, right? Right. So de Broglie derived, based on his hypothesis, de Broglie derived a wavelength for this electron wave, where you can find that lambda, right? Lambda, right? Lambda lambda, right? Lambda is the wavelength of the electron wave. You should keep this point in your mind, where lambda is the wavelength of electron wave. Okay, now already I told you that electron revolving around the nucleus, now onwards we call it as electron wave, and that electron wave has wavelength. Okay, now so de Broglie derived equation for that electron wave wavelength, right? That wavelength is lambda is equal to h by mv, where h is Planck's constant, m is mass of the particle, and v is the velocity of the particle. H is Planck's constant. Okay, lambda is the de Broglie's wavelength. Okay, everything is fine up to this point, everything is fine, right? But what this equation concludes, of course de Broglie derived a equation for wavelength lambda is equal to h by mv. But what this equation concludes and how this equation was deduced, these two questions are very important to understand the concept very clear, right? Okay, so what this equation concludes and how this equation was deduced, let us see one by one, right? How what this equation concludes, right? Right. De Broglie's reasoning. Right. I shall explain how this equation was derived and what is the significance. Right. Okay. De Broglie's reasoning lead to the conclusion that waves can behave like particles and particles can exhibit wave-like properties. Right. I shall insist. I wish to insist on this point. Okay. De Broglie's reasoning lead to the conclusion that waves can behave like particles and particles can exhibit wave-like properties. Okay, and before the de Broglie's hypothesis, we know that electron is a particle, but after the de Broglie's hypothesis, electron is particle. Okay, and that particle can exhibit wave-like properties. Okay, so de Broglie reasoning lead to the conclusion that waves can behave like particles and particles can exhibit wave-like properties, right? So particles behave like wave-like properties, particles can exhibit wave-like properties. This point should be keep in your mind, that particles can exhibit wave-like properties, right? And de Broglie deduced that the particle and wave properties are related by this expression, right? This is the another important point that should keep in your mind. Okay, right? De Broglie deduced that the particle and wave properties are related by this expression. What is this expression? Lambda is equal to h by mv. This is the equation for particle as well as wave properties. Okay, I wish to insist on this point. Okay, this is the equation which explains the particle and wave properties, right? Particle and wave properties, right? Now we shall go further. Right. Next, already I told you how this equation was deduced. Okay. Right. How this in this slide we shall see how this equation was deduced. In fact, actually, before this de Broglie's hypothesis, right, Planck's quantum theory and Einstein's mass energy relations were established. I repeat, before this de Broglie's hypothesis, Planck's quantum theory and Einstein's mass energy relations were already established. So, by using Planck's quantum theory and Einstein's mass energy relation, right, de Broglie deduced the equation for wavelength lambda is equal to h by mv. Okay, so let us see. right? So according to Planck's equation, the energy of the photon is given by the relation. We all know that energy of the photon is equal to h nu. Energy of the photon is equal to h nu, right? Where E is equal to energy, h is the Planck's constant. We all know that the value of the Planck's constant 6.627 into 10 to the power of minus 34 joule second, right? Mu is the frequency of the light. Okay, and from Einstein's mass energy relation, right? E is equal to mc square. E is equal to mc square. E is equal to mc square, where m is mass and c is the speed of light. From these equations, we can find that okay, the LHS of this equation and the LHS of this equation are equal. So we can equate the RHS. We can equate the RHS of the both equations. That is, we can equate h nu is equal to mc square, right? H nu is equal to mc square, and we know that h nu is equal to c by lambda. Mu is equal to c by lambda. Already I gave this equation. Mu equal to c by lambda. When we substitute c by lambda instead of nu, that is, this equation becomes hc by nu is equal to mc square, and we can shuffle this equation, and we can we can write the equation for lambda. Lambda is equal to hc by mc square, and lambda is equal to this square, this 1c and 1c get cancelled, and lambda is equal to h by mc, right? And if the velocity, this is c is the velocity of the light, but when we concerns with the microparticles, whether it is electron or proton, whatever it is, okay, we need to replace the c with the velocity of that particle. That's why in general we write v instead of c, because c is a standard letter to represent velocity of the light, right? So lambda is equal to h by m, and if the velocity of the particle moving with mass m is v, then c can replace with the v, that is lambda is equal to h by mv. Okay, now we all know that the mass into velocity gives momentum, so we can write mass into velocity, that we can write momentum, right? Where p is the momentum, and that is p is equal to mass into velocity, right? So we can write p instead of mv. So lambda is equal to h by p, or lambda is equal to h by mv. So we can write lambda is equal to h by mv, or h by p. This is the de Broglie's equation, and already I told that de Broglie derived this equation for particles as well as waves. How? That we derived the de Broglie's equation. Then what is its significance? That is much more important than deriving this equation, right? What is the significance? Let us go further, right? Right? What is the significance of de Broglie's equation, right? De Broglie's equation is true for all particles. I already told you, de Broglie derived this equation for particles as well as waves. You please wait for 2 minutes. That after that 2 minutes, you will definitely your doubts will be erased, right? Okay, de Broglie's equation, right? De Broglie's equation is true for all particles. De Broglie's equation is true for all particles. De Broglie's equation is true for all particles. It should be keep in your mind that de Broglie's equation is true for all particles, but wave aspect is of significance only with the very small particles. Okay, now you should note this point. But wave aspect is of significance only with the very small particles like electrons. Okay, I shall explain you. I shall give the examples also, right? Now let us compare the de Broglie's wavelength associated with bodies. Okay, we shall compare how this equation, actually de Broglie's equation is true for all particles, but wave aspect is of significance only with very small particles. How it comes, how it is true? Okay, how can we prove this? That is, de Broglie's equation is wave aspect is significance only with very small particles like electrons. How it is possible? Okay, we shall I shall give you the examples, right? Let us compare the de Broglie's wavelengths associated with the bodies, right? I shall give you the examples, right? Right. Okay. Already we derived the equation. Okay. Lambda is equal to h by mass into velocity. Mass into velocity. Okay. Let us apply this de Broglie's equation to various bodies. Various bodies. For example, of a large mass. Already I told you in the introduction to quantum mechanics. I already gave you the example, I already defined the macro objects. Macro objects are the objects which are having considerable mass. Okay. Now let us go with the large mass particles, large mass objects of large mass. Example, suppose a cricket ball of mass 200 grams, that is, you convert it into kgs, that it becomes 0.2 kg, is moving with the velocity of 100 meters per second, moving with the velocity of 100 meters per second. Then the de Broglie's wavelength, how can we calculate the de Broglie's wavelength? Lambda is equal to 6.625, that is Planck's constant by mass into velocity. Planck's constant 6.625 into 10 to the power of minus 34 kg meter square second inverse, and mass of the cricket ball is 0.2 kg, and its velocity is 100 meters per second. When we simplify this numerical equation, it comes out to be 3.3125 into 10 to the power of minus 35 meters. Okay, which is very, very, very small value. Which is very small value, because when we write this standard form into decimal form, we can get 0. Almost 34 zeros after 33125. This, you can imagine how this value is and how minute this value is, right? So which is too small to be measured by any instrument, hence it has no significance. Hence it has no significance. That means, okay, a cricket ball also possesses a wavelength. Okay, cricket ball also possesses a wavelength, but its wavelength comes out to be very small, and that cannot be measured by any instrument. Okay, now, so cricket ball is an example of macro object. Cricket ball is an example of macro object which has a considerable mass. And and one more thing, right? And we shall go with a microparticle of small mass, microparticle of a small mass, right? Small mass. Let us consider of electron, right? Electron, already I told you in the video 1, part 1, quantum mechanics. Okay, microparticle, example for microparticle is electron, proton. So let us consider the electron. Mass of the electron is 9.1 into 10 to the power of minus 31 kg, moving with a speed of 6.6 into 10 power 6 meters per second. The de Broglie's wavelength, then we can calculate the de Broglie's wavelength for the electron. Lambda is equal to h is the Planck's constant, 6.625 into 10 to the power of minus 34, and mass of the electron is 9.1 into 10 to the power of minus 31 kg, and its velocity is 6 into 10 power 6. Okay, when we simplify this mathematically equation, okay, now, which comes out to be 1.21 into 10 to the power of minus 10, or which is nearly equal to 121 picometers, which can easily measured experimentally. So this wavelength can be measured accurately. Okay na? But this wavelength, and in the case of cricket ball, this wavelength cannot be measured accurately. That's why we ignored that wavelength. Okay, but in the case of electron, we can measure the wavelength associated with the electron, right, with the greatest accuracy, right? That's why, okay na, from the these two examples, from these two examples, from these two examples, we can conclude that okay, cricket ball also associated with wave nature, but when we are trying to calculate its wavelength, those wavelength values are very small, and which values cannot be measured with any instrument. Okay na? Right. And electron is a microparticle which is also with, which is associated with wave nature, and this wave nature, electron is associated with wave nature, and the wavelength of this electron wave is can be measured accurately, or can be measured with greatest accuracy. Okay, therefore all moving particles, from this we can conclude that all moving particles, okay, the man who is traveling on the road is associated with wave nature, the car which is traveling on the road is associated with wave nature, okay, the electron revolving around the nucleus is also associated with wave nature. But when we are trying to calculate the wavelength of their wave nature, okay na, so when we wish to calculate the wavelength of the car that is moving on the road, because of its large mass, its wavelength values could be very, very, very low, because it is very fundamental truth. For example, h is here is h is called numerator, and m and b are called denominators. Okay, a fraction get the considerable value, a fraction get the considerable value only when denominator value is less than numerator value, then only that fraction gets a considerable value. But when we consider the cricket ball mass, okay na, cricket ball mass 0.2 kg, 0.2 kg is very, 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 very larger than Planck's constant. That's why usually we get a very small wavelength values, But when we substitute mass of the electron, then mass of the electron is less than the value of Planck's constant. That's why usually we get considerable lambda values for electron wave. Okay, na? Therefore, we can conclude that all moving particles, whether it is car moving on the road or bus moving on the road, okay, also associated with wave nature. But when we are trying to calculate their wavelengths, those values are very, very, very low, and that cannot be measurable by any instrument. Okay, but when we trying to calculate the wavelength of the electron that is revolving around the nucleus, we can find the wavelength of the electron wave with a greater accuracy. Therefore, from the above, we come to the conclusion that de Broglie's relation has no significance in everyday life. De Broglie's relation has no significance in everyday life, since in our everyday life we come across macroscopic objects, because in our daily life we concerns with the macro objects. That's why, okay, de Broglie's hypothesis has no significance in our daily life. Then we shall go further, right? We shall go further. Then what is the counter proof for this de Broglie's hypothesis? Already de Broglie proposed that the length of the electron wave is equal to is equal to circumference of the circular orbit. Circumference of the circular orbit. Circumference of the circular orbit. Length of the wavelength of the electron wave is equal to circumference of the circular orbit. Okay, na? And after that, 2 pi r is equal to 2 pi r is the circumference of the circular orbit, n lambda, and lambda from the de Broglie's equation we can write lambda. We can write h by p instead of lambda. That is this h by p. So nh by p. So 2 pi r is equal to nh by p. When we revert this equation, right? P is equal to, we can write P is equal to mass into velocity. So I write mass into velocity instead of P, right? So nh by mv. So we can shuffle this equation. mvr is equal to nh by 2 pi. nh by 2 pi. Okay, now can you recognize this equation? This is the equation which is given by Bohr. Okay, that tells that electrons are revolving those orbits whose angular momentum is integral multiple of h by 2 pi. Okay, electrons are not revolving in electrons revolving in those orbits whose angular momentum is integral multiple of h by 2 pi, right? So electrons, not all orbits are not possible, whose the circular orbit whose angular momentum is integral multiple of h by 2 pi. In such orbits only electrons are revolving around the nucleus. Okay, so when we are trying to deduce the Bohr's equation from de Broglie's hypothesis, okay, now we succeeded, or de Broglie succeeded in getting the Bohr's equation, right? So this is the counter proof for the de Broglie's hypothesis. This is the counter proof for the de Broglie's hypothesis. I hope you understand this lecture, and I wish to conclude this lecture. Okay, so de Broglie's hypothesis is applicable to all moving particles, but all moving particles or all particles, whether it is macro objects or whether it is micro objects or micro particles. But when we are trying to calculate the wavelength of the macro objects, we are getting very too small wavelengths, so which are not considerable. But when we are trying to find out the wavelengths of the micro particles, we can get the considerable wavelengths, right? I hope you understand this lecture. Okay, and I you know thank you for your attention. Okay, if you really like this video, like, share, comment, and subscribe. Thank you for watching.